Alright, hello everybody, and we're going to be continuing going through some math contests today. We're going to be continuing on with question number 5 of the 2013 Canadian Intermediate Mathematics Competition. We just did questions 1, 2, 3, and 4 in part A, so we're still just looking for that final answer. Let's take a look at the question now. So question number 5. A palindrome is a positive integer that is the same when read forwards or backwards. For example, 1331 is a palindrome because 1331 reading forward and 1331 reading backwards. So just like a palindrome as though it were words, like kayak or bob. So determine the number of palindromes between 1,000 and 10,000. So specifically what we're looking for is palindromes, numerical palindromes of 4 digits. That's what it means. So in general, what does a 4-digit palindrome look like? It's going to look like AB, BA, or ABBA, which is a nice Swedish band. Alright, so let's continue reading on with the question. So, determine the number of palindromes between 1,000 and 10,000 that are multiples of 6. Okay, so we're going to have to think for a moment. We'll think really hard. And we have to come up with, how do we tell if something's a multiple of 6? Well, fortunately, there are ways to tell if something's a multiple of 6 just by looking at its digits. So, for example, if something is divisible by 3, if you add up the digits and the sum of the digits is divisible by 3, then something else is divisible by 3. There are lots of divisibility rules out there. There's divisibility rules for 2 and 5. Divisibility rule for 10, if it ends in a 0, it's divisible by 10. So we're asked to sort of consider a divisibility rule for 6, or find a way, just by looking at the digits of our palindromic number, figure out if whether or not it's a multiple of 6. So how are we going to do that? Well, so to be divisible by 6, there's no straight divisibility rule for 6. It's just a combination of the divisibility rules for 2 and 3. So what are the divisibility rules for 2 and 3? So to be divisible by 2, you have to be an even number. To be an even number, it must end in an even number. So 0, 2, 4, 6, or 8. Those must be the last digits. Okay. How about divisibility rule for 3? Well, I actually mentioned it a moment ago. Divisibility rule for 3. You add up all the digits in your number, so 19, for example. If you add up 1 plus 9, it has to be divisible by 3. 19, 1 plus 9 is 10, not a multiple of 3, so 19 is not divisible by 3. So if we take a look at trying to be divisible by 2, we know that A, our last digit over here, must be 0, 2, 4, 6, or 8. But it's also that same number, since it's a palindrome, A must also be the first digit. So it can't be 0. Since it's definitely a 4-digit number. It's not a 3-digit number masquerading as a 4-digit number. Okay, so we've got some cases to work out. So if A is equal to 2, our number looks like 2BBA. And we want it to add up to be a multiple of 3. So 4 plus 2b needs to be a multiple of 3. Okay? Another way of seeing that is if we divide by 2, now let's just write it out the normal way. Let's not jump ahead steps. So we need 3 to divide 4 plus 2b. But 4 plus 2b, that's just 2 times 2 plus b. 3 can't divide 2. It's a prime number, so 3's got to divide 2 plus b. So what single digits, when we add 2 to them, give us a multiple of 3? Well, b could be 1. 1 plus 2 is 3. 3 is certainly divisible by 3. It could be 4, or it could be 7. And this gives us 3 palindromes right here. And those are the only values of b that work. So there's 3 right there. So our next case. So we have 4BB4. Sum of the digits, so that's 4 plus 4 plus b, that's 8 plus 2b. So if 3 divides 8 plus 2b, 3 is going to have to divide 2 times 4 plus b. So 3 is going to have to divide 4 plus b. So what numbers, when we add 4 to them, what single digits, when we add 4 to them, is a multiple of 3? Well, b could be 2. 2 plus 4, so that's 6. That's definitely divisible by 3. It could be 5. That'll give us 9. 9 is a multiple of 3. And lastly, it can be 8. And that gives us 3 more palindromes. And if we wanted to stop and grab our calculator, we could grab our calculator and test, is 4,224, is that divisible by 6? And we'd check. Here we go. 4224 divisible by 6. Yep, it comes out to be 704. So 704 times 6, 4224. We have 2 more cases to go. So what's this going to look like? 6b, 6. We'll just jump straight down to the condition. 3 is going to have to divide 6 plus b. It's just something we've noticed that we don't actually need to compute the digit sum as is. We just need to check does 3 divide a plus b. And it just depends on what a is. So what single digits, when we add them to 6, do we get a multiple of 3? Well, 6 is already a multiple of 3, so b being any multiple of 3 will work. Now remember, b can be 0 because he's in the middle. A couldn't be 0 because it was at the front, but b can definitely be 0. So we get 4 possibilities for 6. 6006, that's definitely divisible by 6. 6336, 6666, and 6996. And so our last case is going to look like this, 8BB8. We need 3 to divide A plus B. So 3 to divide 8 plus B. So B can be 1, it can be 4, that would give us 12, or it could be 7. Those are the only single digits, and we're looking for single digits for B. And so what does that give us? That gives us 8118, 8448, and 8778. So how many in total do we have? Well, we have 3 palindromes on the previous page. The one that we can't see right now. We have 3 palindromes right here. We have 4 right here and 3 right here. So 3 plus 3 plus 4 plus 3. That's 10 right there. So that's a total of 13. Right, and we were just asked palindromes divided by 6. There wasn't another condition, right? Determine the number of palindromes between 1,000 and 10,000. So that's 4-digit palindromes that are multiples of 6. Well, we figured them all out. We wrote them all out. We did case-by-case examples, and we found out that there were exactly 13. 3 of them beginning with 2, 3 of them beginning with 4, 4 of them beginning with 6, and 3 of them beginning with 8. So that's our list. Nice, clean, neat question. We're ready, we're feeling good, we're ready to move on to question number 6, and I hope you'll join me next time for question number 6.